My name is Deb Marr, and I'm a professor of ecology at Indiana University South Bend, and I'll be serving as the moderator for tonight's talk. So the Our Universe Revealed lecture series includes talks in science, music, and the arts, STEAM for everyone. We feature research and creative work that's being done in our region, and it's an opportunity for us to be curious about ourselves, our world, and our universe. And of course, today we're going to be curious about the universe. This is a partnership between the St. Joseph County Public Library, Indiana University South Bend, and the University of Notre Dame. It's my pleasure to introduce today's speaker, Arielle Phillips. She's received national recognition for her work in physics, her art and science collaborations, and also her community science outreach. Dr. Phillips completed a Bachelor of Science in Physics with honors at McGill University in Montreal. She earned her PhD in physics at Princeton University. She's a fellow of the National Science of Black Physicists and was awarded the 2025 Simons Emmy Noether Fellow at the Perimeter Institute for Theoretical Physics. So this is an institute in Ontario. In recognition for her contributions to modern physics. Dr. Phillips is a faculty member in the Department of Physics and Astronomy at the University of Notre Dame. Dr. Phillips has adapted tools from medical physics to peer into the filaments, voids, and clusters of the cosmic web. Her team has developed the EDGE computational framework to study the distribution of objects in space, the environmental history of these objects, and to understand a galaxy's journey through the universe. She's collaborated with engineers, musicians, playwrights, light designers, and directors for the international artistic collaboration High Z. This is an art science installation that was based on the 2011 Nobel Prize-winning discovery of the accelerating universe. Dr. Phillips is known for her creativity in teaching and has developed courses for non-majors, including the physics of civilization and a science play. She developed the physics program at the Westville Correctional Facility. Since 2013, this prison program has grown from just a handful of students to over 100 students taking courses each year. And then this year, Dr. Phillips, in addition to the Perimeter Institute Fellowship, she's also serving as the 24-25 Idea Scholar for the Flatiron Institute in New York City. And so without further ado, I'm going to turn it over to Arielle. She's going to be talking about dim and deserted places, unveiling the nature of the universe in spectacularly modest environments. Thanks.
Well, I have to thank you for that introduction. It's one of the best researched introductions I've ever had. I was like, really? Oh, wait, that's true. I do that as well. But how did you find out? So wonderful. Thank you so much. Yeah, so I'm a little bit of a rebel. I tend to like to look and peer and kind of question things that other people don't want to spend time thinking about. And that's what has led me over my career to looking at emptier spaces, at dimmer objects, and has led quite excitingly to being on the edge of discovering things about the very nature of our universe, the very fabric of our universe. I don't do that work alone. This is a list of people that I work with, both at the University of Notre Dame and outside. Emily's going to be very upset because I haven't put her there. Emily Engelfowler is the third graduate student who should be there as a new PhD candidate in my group. And a whole bunch of people who are outside of the University of Notre Dame. And we're kind of a bit of a ragtag bunch, because my graduate students and Grant Matthews graduate students keep coming back to work with us. So Ali Snedden is also part of my group. Even though now he's in industry, he keeps a hand in astrophysics. And since he's in industry doing high-performance computing, this is a really nice colleague to have in a computational astrophysics group. Inseng Se, who used to be at the University of Notre Dame, has moved on to Oak Ridge National Lab, where he does quantum computing. And Xinghai Zhao was a student here at Notre Dame, is now a professor at Dalton State College and still working with us. Okay, we've got a lot of problems, but that's a good thing, right? So in astrophysics, we have, and I'll go into that in a moment, we get to receive information from our universe and try to interpret it. And I'm on the side of trying to model and kind of anticipate what that information might tell us. And once in a while, we have a bit of a clash between what I say, hey, this is what you should be seeing, and what the observers say, like my husband, that's not what we're seeing, right? So that gives rise to what we usually call a problem. So the core cusp problem is one of those discrepancies between the profile of material in these small dwarf galaxies in observations and the profiles we'd anticipate from our large-scale simulations, where we put all the matter, we evolve it, and then we see what we would get now, what our universe should look like based on the assumptions we put into our simulations. Missing satellite and the too big to fail are also problems along that line, where there's a clash between what we anticipate we should be seeing if we understand the contents of the universe correctly, and if we understand the kind of movement or evolution of our universe correctly, this is what we should see, so maybe we're not understanding things correctly. On top of that, I also like to look at how different environments affect the evolution of the intergalactic medium. That's the material between galaxies, thus intergalactic medium. I also like to probe or think about what a galaxy's journey is in the universe and how that impacts its evolution. So we might see from the images we get from, particularly right now, JWST, in the past, and currently also HST, we might think of a galaxy as something that's static or that will be where it is now forever. But in fact, most galaxies are in motion in our universe. The galaxies themselves are made of material that is constantly in motion, just as it is in our galaxy, right? So if you take anything away from my talk today, it would be this idea of thinking of any picture you see from now on for the rest of your life, any astrophysics picture you see, think of that as a snapshot where you have a still, right? But in fact, that doesn't tell you the whole picture. So you unveil the whole picture by saying, okay, if this galaxy looks like this now, then probably it has something to do with where the material likes to hang out in that galaxy. Even if it's in motion, there are a lot of stars that are closer to the center, fewer towards the edges, for example, right? So that kind of is a statistical snapshot for those of you who are more scientifically inclined in the audience. Now I'm going to step into the dark spot. All right. Okay, so what's a galaxy's journey in the universe? We'll talk about that. How do different environments affect the evolution of the material that's around a galaxy and moving with it? So the galaxies are not alone. They have this kind of enveloping material that we call the circumgalactic medium, and that moves along with it as it goes through structures. So yeah, lots and lots of motion today. And then more recently, my group has started realizing that we have the tools to start thinking about the observational signature of the dark energy equation. So that's the dark energy is what would cause the acceleration of the expansion of the universe, and as well as dark matter models. So that brings us back up to the core cusp problem. We think that that discrepancy between what we're seeing in the profile of smaller dwarf galaxies, it is due to the assumptions we've made about our dark matter in our universe. So the dark matter is what we think is keeping our structures together. Probably there's 10 times as much of it in our galaxy as there is, approximately 10 times as much of it in a galaxy as there is ordinary matter that we see, that emits and absorbs light, and that we usually put on our periodic tables. All right, so it was always obvious that I was going to become an astrophysicist. You can tell by that first picture up there that I was definitely going to become an astrophysicist, and my friend Ari was definitely going to become a lawyer, right? It's obvious from that picture that that's what we were going to do. And I like to show that because what you might think, the person you think might be standing in front of you today, you might think, well, if you look at her CV, she went to McGill, then she went to Princeton, then she went to Caltech, then she went to Amherst College, then she arrived at Notre Dame, and that is her path. But in fact, most of us, most academics, have a very windy and twisty path to where we end up, both to the science we end up doing, but also how we experience those different institutions, how we end up in those different institutions, is all kind of windy and twisty. And so I want to show you, this me about to start undergrad, right? Also obvious that then it was a little bit more obvious that I was going to become an astrophysicist, mostly because I was admitted to an honors physics program by then. And I also had a fellowship that would allow me to go and do research in astrophysics over the summers, so maybe a little bit more obvious, but maybe not at this dinner. And then this is me just before going to grad school, right? And I like to show this picture because this is my grandmother, and I accidentally took a picture at the exact same photographer that she had used. And so you see that they even posed people the exact same way after all those years. But I discovered that at the end. It was the same studio. Okay, so follow. So I like to give this in case there are some people who want to either become professional computational astrophysicists, or even if you want to become an amateur computational astrophysicist. This is something you could do. So for those of you who are thinking about following a similar journey to mine, this is what I like to tell people. You'll first have to learn to program well in one language. Nowadays, it's Python, but what's coming around the corner is Julia. So you might hear those two, but Python has a lot of tools. Julia is a little like Python, but it's faster. Be prepared. So use version control software and interfaces. This is super dry and not very exciting, but it will get you a job if you decide not to go into astrophysics. But even if you're in astrophysics, my group uses version control software. Be prepared to learn another language. So think of learning a language, a programming language, as kind of an entry point into understanding the structures of how you build a program, and then being able to translate that into another language. So for example, when I was a graduate student, one of my professors said, okay, you're going to be using A for this program. And I said, A? A? I didn't even know that was a language. It was like, well, here's a book, and you'll use A. So I've used in my journey, starting from elementary school with a little bit of BASIC, kind of high school level, Pascal, Fortran, then C, then C++, and now Python. That's what I've had to work with over the years. Download publicly available large-scale simulation codes. Those are available to everyone. You can download them on your laptop and run them. And run them on your computer, or you can also analyze existing simulations, some of which are also available online. Apply publicly available analysis tools, Halo finders, data generator tools. Those are also available to most of you. And then figure out what your question is and what are your limits. The most important thing as a computational astrophysicist you do is not create pretty pictures or the like. It's understanding what the limits of what you put into your code are, what the limits as to what questions you can ask of it are. okay? And then this is super important, well, in astrophysics, but I think it's kind of a general thing. Find a mentor who believes in you and believe them. Keep believing them even when it's hard to believe them, right? Keep believing that, if they believe in you, keep believing them. And then this is also a hard one. If you stumble, give yourself a second chance. Give yourself the chance you would give to a friend, right? Okay, so how do astrophysicists do astrophysics? Well, we do it in nice places very often. So there's this quote that's not at all about astrophysics, but it's about science. And that's from a play, Photograph 51 by Anna Ziegler, that says, scientists make discoveries over lunch. And physicists have understood that, and we like to have lunch in nice places. So we've created these institutes like the Aspen Center for Physics, which is in Aspen, not surprisingly. There's also one in Les Houches. There's the Kavli Institute for Theoretical Physics, am I correct? Right, theoretical physics, right? That's right across from the ocean in Santa Barbara. And then recently I was lucky enough to visit, to take a sabbatical at the Perimeter Institute in Waterloo, Ontario, which is by a lake and a very lovely place to spend time and a very stimulating place to spend time. So from this, other than the beautiful pictures, I want you to remember that most scientists don't do science alone, right? Even if it's just talking an idea through that you're mostly going to do the work for, we usually like to bounce ideas off of each other. And a lot of the time, it's a lot more how a kind of, if you thought of a band, creates a song, where it's not all the same person that's creating all the components of the song. That it's kind of something that emerges from a conversation or from people collaborating together. Okay, so another thing, how is astrophysics done? Well, astrophysics is a little different than other fields of physics in that we don't get to set up our lab. We don't really get to entirely decide what experiment we want to run. We first have to understand what laboratories are available to us, and then how we're going to set up our detectors to actually make use of the laboratories that exist already in our universe. The fun part about that is that we reach scales and energies and temperatures that we reach extremes that are not available to us in our labs. And that's true even for our empty spaces. Our empty spaces are much emptier than what we can manage here on Earth. Right. So, oh, sorry about that. All right, so some of the things that we get, so I've already mentioned, we get things from the universe, we get signals from the universe, and that's light, particles, gravitational waves. Those are the signals we get, and then we get to interpret them and ask, what are you telling me about the universe? All right, I like to show this picture. Can anybody tell me what we're looking at here? At first glance, what are we mostly looking at? It does look like Saturn, right? It is Saturn, actually. Okay. What else can you tell me about this? It's not. It's older. But what else can you tell me about? Is there any little thing that you're seeing show up, if you look, that's a little unusual?
The rings, there's like light particles or something.
Okay, all right. Anything else?
Like the prism or something. Looks magnified right there in the middle.
So it looks a little different than what you're used to seeing as Saturn, right? The hint is that little bit of light that's showing up on the corner there. It points to an event that we had recently, but with a different body. Where do you think the sun is here? It's behind it. Yeah, we're seeing a Saturn eclipse of our sun, seen by a satellite, right? But the reason I show this is because of another thing that we're seeing, another object that's very familiar to us, but this perspective is not that familiar to us. So I'd like you to look just above the brightest parts of the disk. There's a little dot there. Do you see that little dot over here? What do you think that little dot is? That little blue dot. So if you go,
Oh my God.
yeah, that's our Earth. So, like to show a different perspective. A lot going on in this picture. Okay, so we just interpreted this picture, right? We just interpreted a whole bunch of things happening. That little diamond ring effect is probably from a prominence, right, on our sun. And this is what I like to show around this. This was from an Edward Tufte lecture who talks about information design, but he showed this manuscript by Galileo, and particularly his first explanation of what he was seeing when he saw Saturn. Right? Saturn looks like this. It's not a perfect celestial sphere, right? It has these elongations that he tried to explain. Okay. Okay. So one of the things we detect is light. And light is both very slow and the fastest thing we know. Right? It's very slow because, and this is good for us astronomers, but it's very slow because it only goes 300,000 kilometers per second. Right? And that means that when you're looking at me, you're receiving light from me in the past. Right? You're not seeing me. You're getting you're getting a whole bunch of history here while I talk to you. Right? My sound takes even longer to get to you. So you're seeing and hearing me in the past. It takes about 30 billionths of a second to cross a room. So when you look at yourself in the mirror, you look at a younger self. Sometimes it's fun to do that. Right? So you're looking, so the good part of that is that looking far away means that we're looking back in time. And so we get to see the universe as it was when it was younger. How do we see? Well, we see with our eyes. We have brightness sensors that tell us how much light we're getting. And we have color sensors that tell us which part of the electromagnetic spectrum we're seeing, or color. Right? We see with 3 light cones, and we particularly tell between, well, we see through 3 filters, and we tell the color of light by comparing the amount of light we get in each of those filters. In particular, when you're telling between red and green, those 2 filters overlap quite a bit, as you can see over here. So I have a primate and a turtle. Do I have a human? Okay, all right, I had changed it for some reason, and all right, so we're closer to this. We have 3 filters, but we don't, yeah, all right, there are other filters. But we have 3 filters, and our red and green are kind of overlapping. So it's not that we actually say, oh, okay, ding, 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 I have red light, ding, 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 I have green light. It's that our brain is actually constantly processing which amount of light you see more of. So that's one of the ways that we see, that's one of the ways we see light. We're not the only ones who have cones, but other beings on our Earth often have more. And in particular, birds and insects tend to have an extra cone that's in the UV, and that allows it to see the world in a very different way. So this might be what we would see, and this is a recreation, as best as people can tell, if you add the UV light. The UV light tends to highlight places that you want those birds or those insects to land. And the reason why you have that is for a very kind of astronomy-related reason. And that's because the Earth is bathed in UV light, right? So with that extra cone, you're just seeing brightness everywhere, right? And so if you want to attract, you have to have these spikes in UV light to particularly catch the eye of these birds and these insects. Okay, so can you tell me what you're seeing here? Okay, absolutely. What else are you seeing here? Red and green, correct. So you see anything else you're seeing in this picture?
Highlight.
Okay. Anything else? Is there anything else in this picture? Okay. So there are only tomatoes in this picture.
What's flavors?
They're stems. Are these tomatoes kind of free floating in space? Ah, they're in a basket. Okay, so all very good answers, right? You see red, you see green, and you see, using your incredible processor and your structure finder in your head, a basket, right? Now, if I were to reproduce what you just did to figure out that there's a basket here, right, which all of you see now that you know what I was trying to ask you, right? If I were to recreate that, that's actually very hard because there's a little bit over here, there's a little bit over there, there's a texture, there's different light in different, so we go much dimmer here than we go over here, which is really brightly lit. Right? We have just two tiny little pieces of basket, but you were able to figure out that these tomatoes are not free floating in space. Right? They're probably earthbound and they're contained. Right. Okay. The other thing is, so you're seeing reflections, you're seeing a certain amount of light coming from this, you're seeing color, but you're also seeing every other color but red tomatoes. Right? Because the red light is actually being reflected off of the tomato. It's not actually being part of the tomato. Right? So that kind of analysis that we just did on these tomatoes is what we do over and over in astrophysics, right? So I talked about seeing the light, figuring out what you're getting, measuring it so you get a brightness, understanding which part of the electromagnetic spectrum you're looking at, that's color. We enhance those with our tools in astronomy, right? Then we used a tool that I use, which is a structure finder, right? But it's in our brain, and it's very good. We're very good at finding patterns and reconstructing this arc, right? Which is not at all obvious to do this, okay? So actually a good part of the history of astronomy has been improving what we can already do with our own bodies. Right? Good part of the history of astronomy, I was showing Galileo, he looked through a telescope, but with his eye, not with a detector, not with a photographic plate, obviously not with a CCD, right? Not with a charge-coupled device. He was looking with his eye and recording what he was seeing, and that's a good part of the history of astronomy, right? So he was enhancing his eye with a telescope so that he could see dimmer objects. All right, okay. So we enhance our vision. We want to see dimmer objects that are often further away from us, and that allows us to travel back in time in what we see. It allows us to discover dimmer objects, hidden corners of our own neighborhood, so the dimmer things that are floating around us or orbiting around us. And it allows us to uncover hidden parts of our universe. We enhance our vision both in terms of how dim we can see, but also in what parts of the electromagnetic spectrum we can see. So we don't, the part that we were looking with is just a part of the electromagnetic spectrum that we probe with all our tools. Okay, and then what we do with all of this enhanced detail about the light is we figure out what the light looked like originally when it started heading our way and what happened to it on its way to us. Who can tell me what this is? Okay, but if you were to quickly have to tell me what this looks like, what does this look like from non-scientific point of view? Yeah, it's definite. It's not just a rainbow, it's the rainbow. It's the light from our sun. So this is exactly a rainbow that we would get here on Earth, right? Which is just sunlight spread out, right? So this is the actual rainbow. Obviously, it's enhanced, right, from what we get to see when we use a hose in our garden and it sprays and then we see a rainbow. We don't see with this detail. What are you seeing here that you wouldn't normally see in a rainbow nearby?
All those horizontal and vertical lines.
Yeah, there's these lines. So the horizontal lines are basically just me creating this extremely long rainbow into a readable format. So it's like a book, right? So I start in the blue and I read across and then I go to the next line and I read across, and then if I wanted to create this rainbow, I could cut up all of those horizontal lines and glue them next to each other, and that would be the rainbow. I would recover a rainbow, right? So this is basically rainbow in book format, right? But the vertical lines, I wouldn't get just by looking normally at a rainbow in our everyday lives, right? And those are actually missing light. Those are missing photons that were headed our way. They were kind of happily heading our way. And then they interacted with the outskirts of our sun. And by the time the interaction ended, they got turned around and they headed in a different direction and never made it to us. Okay, so that's what that is. Okay, so this is a less romantic view of the electromagnetic spectrum, right? And that rainbow is just in the visible part of our spectrum. We now have tools to look blueward or in higher energy, so in the ultraviolet, X-rays, and gamma rays, and then redward or less energy in the infrared, microwave, and radio, right? And we as humanity preserve some windows in each parts of that electromagnetic spectrum so that we can continue to learn more about our universe. Another variable. So I've kind of implied two more things that I want to highlight about what we observe before I tell you, okay, but let's actually look at our universe, okay? And that is time. Okay, I'm going to shorten this exercise I do in my class. Okay, so I want to convince you that, okay, I've already convinced you that you can see, right? Those of us who can see, right? Those of us who can see multiple colors, but not everybody can. But you're convinced of that, mostly because you're watching my talk. I've convinced you that you can hear. But I haven't necessarily convinced you that you actually have an understanding of time within your own body. So this exercise I do in my class to convince my students that they have an understanding of time in their own body can be done one of two ways. And that is, you can either stand up at the end of 30 seconds, or you can lift your arm if you don't want to stand up, which is perfectly fine. Okay? So 30 seconds, you can measure them any way you want, except looking at your phone or your watch. All right? And there's no timer on here, good. Or any clock in here. No, don't look at that. Use some internal mechanism to count to 30 seconds, and then either stand up or put your hand up, okay? And then I will stop this exercise once everybody has done this. Now, if you're somebody who's vulnerable to peer pressure, you are allowed to close your eyes for this, right? Because once people start standing up, it feels a little bit like, oh, I'm gonna be left behind. I'm gonna be the one who's like here for 2 hours with my, right? That has never happened in my classroom, okay? Nobody has been like, wait, don't end this class, I'm still counting, okay? All right, okay, so we're gonna start now. Okay, we're gonna stop here. Thank you very much. So it won't astonish you to know that you were within, I would say, plus or minus 5 seconds of 30 seconds, okay? If I leave at the end of this talk and say you have to stay here for 5 more minutes, if I come back tomorrow morning, none of you is going to be here, right? And it's not because you're impolite. It's just because you will know that you've gone past 5 minutes, right? We have an innate sense of time. Now, some of us might have used techniques. So what are some of the techniques you use to count to 30? Tapping your foot. Now, what background do you have that allows you to tap your foot? There you go. Yep. Do we have any athletes in the audience? Mm-hmm. What technique did you use? Okay, you just counted. Some of my athletes sometimes will use their own pulse because they know what their resting pulse is. And so they'll use that. All right? So all of those techniques are things that we've learned, right? But we also don't count 1 Mississippi, right? No one did that in this. So we have an innate sense of time. Also, you made it here, so I want to convince you that and we're not going to do an exercise for that, but you have an understanding of motion, of vectors, right? You had a velocity and a direction to get here tonight. And nobody's going to get here 3 hours after my talk because they were walking super slowly in the wrong direction, right? That's not going to happen. Convinced that they were going at a correct speed to get here, right? Nobody's doing that. Right? So we have these innate understandings, and what we're doing is enhancing our way of measuring these things. Okay. Okay, so let's get to what I do and what we're doing. So we look at objects in astrophysics using every single tool we can. So if you create a technology that we think we can use in some way to look at our light, to do something that's related to our light, to send our data to each other. We have all of the types of storage you can imagine in our offices, and they're only as old as we are, right? So they'll go back to whatever type of storage we'll have used every communication type. There is a whole history of part of astronomy that was done on fax machines, using fax machines. Not everybody in this audience will know what that is, but using fax machines. And so our history is really one of we see the brightest stuff first and the dimmer stuff later. And often the dimmer stuff is what's really interesting, and it's the mark of a mature field. So you can see this in these progressions from COBE, which first detected the cosmic microwave, first measured the cosmic microwave background, to WMAP, which could see the different fluctuations in the cosmic microwave background, and to Planck, that can see even more detail. Okay? And then my field uses completely made up universes using computational astrophysics. And the only thing that keeps us from going completely bonkers is that we actually have to follow the laws of physics and come up with something that is realistically what we might see out there. And so we use kind of signposts to think, okay, am I getting this right? In this particular simulation by Matthew Bates, you're seeing the creation of stars. So those little dots is that the physics in that region was such that we anticipate that a star could be created there, and then it moves around as a star. Okay? So if his simulations did not create stars, right, either he would think, if his simulations did not create the conditions necessary to create stars, so he's not actually creating stars because that would require resolution that's much higher than that. But if it didn't have conditions that could foster the creation of stars, you'd probably think I don't quite have this right? If I'm looking at a star-forming region and I don't have anything that could form stars, I'm probably not correct. Okay? And that's part of what I do. Okay, so we are able to use all of these tools to start looking at objects at different scales. And we use those to look at things like the nearest galaxies that are kind of 2 million light years away, or about a megaparsec. We look at clusters of galaxies that are maybe on the scales of 100 million light years. So this is a cluster of galaxies, the Coma cluster. And we use this information in computational astrophysics to kind of serve as sanity checks to make sure that our ideas of how our universe might form, the physics we put inside, the material we put inside, corresponds to what we see. But I've gone in a very short while from all the way from looking at a place where stars might form and telling you that even there, I'm not actually following a real star, right? I'm not then simulating the star and looking at how material, maybe there's convection, how material moves through that star. I'm not doing that. I'm just saying a star formed and now it's moving around, right? I might attach a history to it and say, okay, well, it's fusing material in it, so I'm going to follow that. But I'm not actually going to computationally look inside of that star. That was a star-forming region. Now we're looking at things where we're forming more like galaxies, right? So we're definitely at that point not looking at individual stars in those simulations. So that's another thing that we have to keep in mind. Our universe has these incredible scales, right? We go from teeny tiny, that's like the size of our sun, which we don't usually think of as teeny tiny, right? To things that are huge, that would take 100 million years for light to travel across. We have multiple ways of looking at those large scales in our computation. So we have two different ways that I like to let you know about. How do we create a universe in a box, given that you have those limits? Well, first you start, and this is kind of called the Eulerian way of doing computational astrophysics. You start with a cubical lattice, you add baryonic fluid and dark matter particles, so you have a fluid and dark matter particles, and some initial conditions. So remember I showed you those maps of the cosmic microwave background? Those have the imprint of the first fluctuations in our universe. Without those fluctuations, we are not here today because we don't actually form any structure. We don't therefore form stars and we don't actually form the materials to make us if we don't form stars. So you add initial conditions, you apply the law of physics, you make star particles, as I discussed. You have the conditions that allow for stars to form, but you don't follow the stars themselves. And then you track all the outputs in individual cells. So you're kind of standing in a cell, and you have some gas, and you have some dark matter particles, and then you kind of look, oh, is any gas joining me? Is any of my gas going away? Right? And you do that for all those different cells. Okay, there's another type of simulation that we use. Oh, right? So you repeat, which is called a Lagrangian simulation. In this case, you just have particles. So you have dark matter particles, but you also just have baryonic particles if you're interested in that. In this case, we're looking at dark matter particles, and we're looking at the illustrious simulation. The previous one was the ENSO simulation. Those are commonly used simulations, and if you're interested in following the path I outlined earlier, you might look up those two simulations. So in this case, you're following dark matter, but you're also able to figure out the baryonic matter and look at, for example, on this side, the gas temperature. And you're seeing outflows. Do you see how sometimes you have like a bubble that forms and you have hotter gas going out? So you're tracking all of this physics, sometimes this shock physics, and seeing where this material goes, what energy it injects around it, and how the temperature varies as a result. Okay, so now you've seen that you have those simulations, that there are some places where we just put in the physics and we let the physics do its thing, and there's sometimes where we have to apply rules and say, oh, the conditions around here are okay, I'm going to be forming stars, right? And so depending on what part of the physics you're interested in probing, you're going to be doing that. You're going to have the physics, and then you're going to have the rules or the recipes that are combined to create your simulation. This is Ali Snedden, who was my graduate student. He ran one of the codes that's publicly available, Gadget 2 code. He added a whole bunch of physics because of what he wanted to study. So he added baryons. So he added ordinary material on our periodic table. He added radiative cooling. So that's the effect of radiation and losing some energy through radiation. He added star formation through a recipe. He added nucleosynthesis, knowing how fusion might take, what rates of fusion might take place in a star, what elements you might create. He added supernova feedback, so that's both ejecting material and energy, right? And then that allowed us to look at the universe on those larger scales that are illustrated on this side. So you're seeing, again, those kind of higher density regions and those emptier regions. To look at the specific structure, we use what is called an algorithm, but a structure finding algorithm. And that allows us to make a bridge between our simulations and our observations. And initially, the algorithm we used was used in computer vision to detect vasculature in the brain. So you can see, and you'll see in a moment, why I might have been interested in porting this from a medical setting to an astrophysics setting when I start thinking about filamentary structure, particularly if you look all the way up there, right? Some of the structure kind of looks the same. Okay, and this should further convince you. So here we have sheets. So these are structures that are sheet-like. Like a sheet in your home. In 2 dimensions, they're very long. In 1 dimension, they're very short. Right? Here you have filaments, long in 1 direction, short in 2 dimensions. And then groups or clusters that are short in 3 dimensions. And our algorithm actually looks at how that density is changing and not so much at what the density is. And so it kind of looks at the second order derivative of this. And then we're looking at other ways of finding structure, but I want to get to what we do with this. So I kind of tried to make it look simple, but I also like to sometimes with my students show that it's also complex. And so when you're doing a full set of simulations and you're also analyzing those simulations, you end up with all kinds of different codes and algorithms that you use to try to answer the question that you're asking. Okay? And that brings me to the questions that I'm asking. Okay? So I told you right at the beginning that I don't tend to look at the big structures in our universe. This is a symbol for a cluster of galaxies. Material is falling into that cluster. It's a big, bright object. There's lots of galaxies. There's lots of gas. You can see it in all kinds of bands, all kinds of parts of the electromagnetic spectrum. So, you know, why bother with things you can see a lot, right? Instead, from an early time as a graduate student, I was like, let me look at things we can't see yet, right? So filamentary structure. So I'm designating it this way. Or voids, things that behave in a weird way. They empty out, they don't fill up, right? They spend the whole history of the universe just emptying out. Or maybe these little kind of modest, dim galaxies like dwarf galaxies. And those are the things I'm interested in. Okay, why might I be interested in looking in those places? Well, here we can use, okay, so here I'm using graphs, right? I want to put graphs in my public talk, but if you don't want to look at graphs, you can just look at these little symbols here. So what am I telling you here? Well, around here is emptier space, and around here is denser cluster-like space, okay? And what we're seeing is that there are two different types of galaxies, the spirals and the ellipticals. So this is telling us less material, more material, and this is just telling us how many galaxies do I see? Okay, what fraction of galaxies do I see at those densities? So now you can look at and understand a science plot in astrophysics, okay? So what you're seeing is that you have ellipticals go up. So you have a bigger fraction of ellipticals in a dense environment than you have in a low density environment, and spirals kind of come down, right? They spiral down, ha ha ha, no. They come down here in density, and so what you're saying is you have more spirals in emptier spaces and fewer spirals in dense spaces. So we know that environment will impact the morphology of galaxies, the actual structure of galaxies, which, if you remember from earlier on, I told you is actually a snapshot of what's going on in the galaxy, right? So material is moving around, and we're kind of seeing where material tends to move around, okay? A little bit like if you took a snapshot of a quad on your university, right? During, between classes, right? None of those students are going to stay there, right? They're not going to be there the next moment. They'll have moved on, but you can tell that, oh, they're walking a lot along the pathways, okay? On our Notre Dame campus, what the people who are in charge of our grounds discover is that, oh, the students also don't walk on the pathways, and so a new pathway is built where the grass has completely died because this is a shortcut to a certain classroom, right? So you might even have the remnant of information about where something was, in this case, students. All right. We also know that going from doing a transition from one type of structure to another, this is a galaxy that's falling into a cluster, but it's leaving some of its gas behind as it does that, right? Some of its gas is leaving it as it's falling in. Galaxies also might transition from their original morphology, their shape, to a different one as they move from one type of structure to the other. Okay? We also know that galaxies tend to align in different ways along filaments. So here you have another plot. Don't look at the plot over here, but look at this plot here, right? What are you seeing with the little lines and this long line here? If you look at the little lines, are they aligned with the longer axis here, or are they anti-aligned? Anti, yeah, absolutely. So we found that galaxies tend to spin, right? The spin axis tends to be anti-aligned with the main when they're more massive. So we're discovering that the environment even has an impact on which direction you're spinning and how you formed to be spinning that way. You've just interpreted another graph. Again, if you don't want to be interpreting graphs, this is galaxies and filaments, okay? Okay, right, so we're discovering that. And then we're starting to just see this gas along filaments in these kind of less dense environments. So we're seeing it in one part of the electromagnetic spectrum, in Lyman alpha emission here. And you're seeing kind of this kind of elongated structure. So you see that there's an image with kind of an idea of how many photons you're getting in different places. And then there are contours that have been created to show where that light is more concentrated. Here you have, in a different way of looking at it, we're looking at pairs of galaxies, and then we're looking at if there's anything in between those pairs of galaxies. So we're like, I see this, I remove this, because I know what the galaxy should look like. I see if anything is left, right? And they're seeing material that could be along those filaments. So another reason to look at filaments more around here. And then this I don't actually want you to interpret. But what this is just looking at the sizes of voids, so empty regions in our universe, and saying how many of this size do I have? How many of that size do I have? How many of this size do I have? And how many? So the same thing as we did for galaxies just a while ago, but for voids. And here the x-axis is the size of the void, right? So this is number, just like our plot for galaxies, but this is different in that we're just looking at the size of the void. And we see that different sizes of voids give us different so different distributions of sizes of void correspond to different cosmology. Okay, I think I've run out of patience with plots, so I'm going to go to not plots and talk a little bit about what we're discovering. So this is some work that I did briefly with my husband there. One of the only times, even though we've had long careers in the same field, where we've collaborated together, right? And this was looking at a galaxy that's in a void versus a galaxy that, we were looking for galaxies in voids. And so why are those places that interesting? Well, with everything that I've talked to you about up till now, you know that, first of all, emptier spaces versus more populated spaces will lead to different shapes in your galaxies, right? But here's another thing. I told you about the motions of everything, how things evolve, right? We saw material collapse in our large-scale simulations. So if you're in an emptier space, you'll have access to less material. You'll have less material that can collapse into your structure. And you'll have less material with which you can create stars. So remember those conditions that are good for creating stars. And so if you look at a galaxy in a void, it has been in a less populated environment, and so it's kind of interesting to find out how it forms in that environment. It's also interesting to find out what happens to galaxies as they stream along filaments. So this is work that my graduate student, Emily Engelthaler, worked on. What she did is she looked at galaxies close to filaments in the past in cosmological simulations, and then she followed them and saw what they were doing. Now, this might trick you a little bit because of course, if you follow one galaxy and you look at its path, it will look like it's going along a filament, right? Because it's just its path, its trajectory looks like a filament. But so you will have to trust me that they stayed along those filaments. So here's another reason why you might want to look in those dimmer places at galaxies and to figure out how they form and what happens to them. It's because most of our galaxies are actually in that environment. A lot of them are, right? especially when you think about the spirals that we were looking at that are in emptier environments. Okay. Do I want to do that? Okay, all right. Here's another thing that we saw here. You don't have to interpret a graph at all. What we saw is that these are all little galaxies, and we're looking at where they're moving to, okay? And we see that they're kind of streaming towards this area. And at some point, they stream so much that their environment actually changes. It goes from something that's more like a cluster to something that's more like a giant filament. Now, why might we be interested in that? Well, we're interested in that because of that graph that you interpreted for me, right? Where you said, okay, in a filament, galaxies tend to be aligned differently. That's probably because of the material and how it accretes onto the galaxy, how it joins that galaxy, right? And we said, oh, okay, they look to be anti-aligned, so that orientation of the filament is having a really big impact on that galaxy. And that's what, so if we go from having a galaxy that's in a cluster-like environment to a galaxy that's in a filament-like environment, that's going to change its evolution over time because of the material that it has access to. Okay, let me see. Just want to wrap things up. Okay. So, to summarize, I'm not going to summarize this. I'm going to summarize myself. I think we're good for summarizing now, okay? Yeah, okay, good. To summarize, what you've seen today is that we have all these tools that enhance our natural ways of experiencing the universe, right? We have an experience of the universe. We can even see parts of it just by eye. We can experience some of it, but we, as astronomers, create these tools that allow us to enhance that vision of our universe, right? I work in a field where we do simulations. You now have knowledge about simulations that you may not have had coming in. You know that, first of all, they're publicly available and you can run them yourselves if you feel like it and want to learn about it. You also know that we don't put everything in there, right? We put kind of a type of dark matter. We put some physics. We put an understanding of how the space and time function. But sometimes we need recipes that are like, basically, I can't deal with that right now, right? I can't deal with that. Star is formed. It's going to move around. But I can't go and look at what's happening in the star itself, right? Because I don't have the resolution in my simulations. So not everybody knows this, right? When they see large-scale simulations, they might even imagine that we can, eventually populate our planets around our stars. But we cannot. We don't even have individual stars very often. So that you know. Now, you also know that what tools we use, right, in that complex map that I showed you, what tools we use have to do with the question that we're asking, right? So we don't use, and that we have to keep very much track of what questions we can and cannot answer using our simulations. And you now know why I'm interested in the dimmer places and the smaller places. So dimmer places because that's often where there's that kind of tension between what we observe in the universe and what we're seeing in our simulations, and the deserted places because that's where most of the galaxies in our universe actually reside and spend their time, right? And that being in that kind of environment is going to have a huge impact on what happens in that galaxy. All right, so that being said, I'll leave you with this, and this is a poem by Rebecca Elson from her book, A Responsibility to Awe. And this is dark matter. Above a pond, an unseen filament of spider's floss suspends a slowly spinning leaf. Thank you very much. So what you're seeing here is the actual distribution of galaxies in our universe. This is a Sloan Digital Sky Survey animation. The actual galaxies that are there, of course, are painted on, but their positions and their types are from our actual observations. And so you can see in those butterfly wings that there's parts of the universe that are missing, and that's just because they've looked along a strip of sky, and then they've told us everything that's in that wing. All right, any questions? Yes?
So you were talking a lot about like vision and how like we'll always see in the past because we just like, we're not doing the process fast enough. But what if you could move at the same speed that that light is being transmitted? Could you then see like closer to the present in these like farther stars, or is it just about your brain process?
So it's not your brain, it's the actual light is taking a while to get to us, right? So 30 billionth of a second doesn't sound like a lot, but when you have very long distances, you start having things that take 4 years to reach us, or 100 years to reach us, or 100 million years to reach us. So it's not so much our brain processing speed, because most of the time we're not just looking with our eyes anymore. It's more that the light took a long time to get to us. So even in this room, the people that are closer to you, you are seeing in a more recent past than you are seeing me. Right? So what was the second part of your question?
So if we were to move faster towards those things and like almost, I guess it's impossible, but if you were to match the speed at which it's being transmitted and you were also going towards it, like would you see it in the present?
So I think I'm going to reinterpret your question, but if you're not happy with the way I reinterpret, I'll come back to it, to be a question that we ask ourselves of what if the speed of light were infinite? Like what if it got to us immediately? All right? So moving, we can't move anywhere near the speed of light, so it's not going to change very much, except that the objects we look at will look like they have a slightly different spectrum, so everything would be shifted. Because of motion. So if we move relative to the light we're trying to look at, the spectrum will look a little different because things will be shifted with respect from where we see. Because it will be just like that source moving with respect to us. What I will say is that we often think about, what if I could see everything in the universe right now? Like all the light just gets to me now, of stuff that's out there right now. Well, you'd see a lot of things that are much older than what they were before, right? Because our universe is quite old. And so that galaxy that you see from far away that looks like a young blue galaxy that's forming all kinds of stars has probably run out of gas. It's not forming stars. Maybe it's interacted with another galaxy and its orbits have been all disrupted, and now it doesn't look the same as it did before, right? Some things might even have disappeared that we see now, but they're no longer there. Okay, there was another question. Yes?
I was just wondering, for those dark matter simulations, like what data is that based on? Like, if like how are we getting dark matter data to run to?
So, we're getting the dark matter data that we have is in how objects move, for the most part. How objects moved and how objects have collapsed. So we see it in the motion of material in galaxies, the motion of material in clusters of galaxies. We also see it in the fact that we formed galaxies by now, right? So initially those little fluctuations that are the seed of structure formation had to have dark matter in order to form material now. That's not that much information to go by, right? It's like, okay, there's something that does gravity, right? There's something that adds mass to our, and we don't have a lot of other information about it. So then we turn to people who are theorists who think, what could it be, right? And one of the things that has been posited is what we use in most of our simulations, which is called cold dark matter. It's dark matter that doesn't like to interact with each other. They're really kind of introverts. They go around and don't interact very much other than gravitationally, right? Cold dark matter is what you'll see in most of those simulations, and it's a type, the way we put it into our simulations is by its interaction with itself. That's how we That's how we put it. But if we discover that it's something else, we'll have to change all of our simulations. Something like that happened in my graduate school, while I was doing graduate school, in that, unfortunately, then my fiance's group discovered that the cosmology of the universe wasn't what I was using in in my work, and so I actually had to change my work to make allowances for
doing
this.
my job.
Yeah. Well, I mean, it was a wonderful Nobel Prize winning discovery, but, it was also annoying. I had to redo my work. So if we discovered that dark matter behaved differently, then we'll have to redo those simulations. My group is also looking at self-interacting dark matter. That's dark matter that's less unwilling to interact with itself, and that's one of the models that we're looking at. There's also a type of dark matter that's fuzzy dark matter. A lot of those are just when or how they interact is how we're modeling dark matter. But we don't actually have a particle, like a particle that you attach physics to. And just say it's that particle, so therefore it will behave this way. We have a model. Any other questions? Yes?
You mentioned, I think, that most galaxies are in the dim and deserted regions, but we live in the Milky Way, which is in the local group, which is in the Virgo supercluster, Laniakea supercluster, etc. And so does that mean that our galaxy is not normal?
So we're not in a cluster of galaxies, so we're not in the most abnormal. We're in a supercluster, but we're not in a cluster. We're in a fairly sparse region, given that we're in a local group. So group is a form of a set of galaxies that are together. So that would be what we're in, as opposed to a cluster. So a supercluster tends to be a chain of clusters and groups that are all together. We're kind of in a slightly more dense place than average, right? But not in the densest places. Yeah. Good question. Anything else? All right, well, thank you very much for coming tonight. Did you want to?
Sure. So why don't we have a round of applause for so we have a couple more talks coming up. So at the beginning of April, we'll be having a book launch. So this is The Color of North, thinking about molecular language, so diving into biochemistry. This will be by Shahir Risk and Maggie Fink. And then in May, we're going to be going to baboons. And so thinking about how the social life of baboons affects their survival and risk of getting disease. So that's what we have coming up. So first, April 1st, April Fool's Day, biochemistry. May, we're thinking baboons. So, thanks so much for coming.